these are systems of linear equations. And when we look at this, it says, is negative 3, 1 a solution to the system? A solution to the system would mean this, is that x equal negative 3, y equal 1 works in both equations. So a system is two or more equations. If you have two equations, you'll have two unknowns. And if you have three unknowns, you normally have three equations. If you have four unknowns, you'll have four equations. In the sciences, lots of times that's what you'll run into, is more than two unknowns. And it says I'm going to check, and I'm going to label my two equations. Here's equation 1 and equation 2. And then I'm going to do a check of x equal negative 3, y equal 1. And if I use equation 1, which is x minus y equal negative 4, that says if I put in x and I put in y, it should equal negative 4. Negative 4 equals negative 4, and it checks. So it is true in equation 1, but it's got to work in both. If I look at equation 2, is 2x plus 10y equal 4. If x equals negative 3, I'd have 2 times negative 3 plus 10 times y is 1 should equal, I want to know, is it equal to 4? This is negative 6 plus 10. Negative 6 plus 10 is 4. 4 does equal 4, so it checks. So the answer would be yes. Negative 3, 1 is a solution. It worked in both. Now there are three types of solutions when we go to the graphs, and this is why you check it out. One type is where I draw a line, and you just draw a line anywhere on your paper, and I draw a second line, and the two lines cross at a single point. That's what happened to the problem above. If I were to graph those two graphs would cross at negative 3, positive 1. That's this. So it crosses at one point. Its type is called consistent. The number of solutions it has is 1. So when you're looking at a solution, it's going to be an x, y value that makes both equations true. So it's a shared x, y value. It's a shared x, y value. I can have it so if I draw a line, and I draw a line which is parallel. Parallel lines never cross. Parallel lines never cross. So as a result, the type of solution I have is inconsistent. Number of solutions, 0. Now, in English, in as a prefix means not. So consistent, if I put in front of it, not consistent means it does not have a solution. Consistent means it has a solution. Not consistent, it's like rational and irrational. IR in English means not. So I have rational numbers, and if I put IR in front of it, irrational numbers means they are not rational numbers. So the prefix tells you a lot. Everybody get the roll? Finally. And then we have it, so if I draw a line, I draw a second line, and the lines are on top of each other. Each other. They are the same line. Now, what do the two lines have in common? Each other, the whole line. The type is dependent. And the number of solutions is infinite. Now, I can tell you right now, this is a test question. I will give you the words, and you have to put them in the proper blanks. There are three methods of solutions. One is graphical, and that's what we're going to investigate today. It's a graphical solution to the system. It is the least good way of getting a solution, because if your solution is like 2 1/3 and 1/2, how do you know? Because your pen point's wider than that. However, I often use it in terms of checking my answer. I'll use my grapher. I'll graph the two solutions on my grapher, and if what I get by pencil paper algebra is what it looks like somewhere around, I usually call it Mr. Rogers' neighborhood. So in other words, I'd be close to what the answer appears to be, then I know I'm okay. Does it look like it's -3,1? Is that close to -3,1? And if it is, I say, well, I'm probably okay. So it's kind of like a little cross-check when I'm doing things. But graphical solutions are really not the way to go in the end. So that means I need to graph these two. The easiest way to graph this is using the intercept method. If you try to use the slope-intercept method, that certainly would work, but it's much less satisfying. But I do have a problem, by the way, with the intercept method on this guy right here. I need to change my graph paper is what I need to do. So, huh?
Because it goes off the graph.
Because it goes off the paper, yeah. And for the graphical solution, you need to be exact. As exact as you can get it. So if I look at x minus y equal -4, I'm going to go ahead and just use the intercept method. So x equals 0, y equals 0. So if x equals 0, I get 0 minus y equals -4. Minus y equals -4, or y is 4. Now normally what I do is I come up here, I cover the x up because it's 0. Then I notice minus y equals -4, so y equals 4. And if y equals 0, I get that x minus 0 equals -4, or x equals -4. So my first line is going to be 0, 4, and -4, 0. And then this is where you really do need a straight edge of some form, and something which really is a straight edge. So sometimes I'll fold a piece of paper in half and do it that way, if I can find something that looks like it's fairly straight. And as best I can, draw the line. This is why trying to do this thing graphically ends up being so messy. Because if I'm off just slightly, I'm going to have a heck of a time reading my answer off. So this would be the graph of x minus y equals negative 4. So this is equation 1. Equation 2 is x plus y equals 6. Now my graph paper is not going to help me, because if x equals 0, y equals 6, I only have 5 units on my graph paper, both directions. And if y equals 0, x equals 6. So that's not going to help me at all. So what could I do? Well, I'm going to solve this, and for y, put it in slope-intercept form. And I could say, well, the intercept is 6, but I'm still off my graph paper. But if I'm going to try to do a 6, I better be very, very careful to make sure if x equals 0, y equals 6, that that looks like, if that grid were there, that's where it would be. Then I go down 1, because here the slope, so b is 6, and the slope is negative 1. That means that it's rise over run. So I'm going to run 1 and rise negative 1. So I'm going to go over 1, down 1, and let's hope that's what the solution is. Because I just landed on top of the line I just drew. And then I'm going to draw the second line. In fact, I'll draw him in red. So this is the second equation, x plus y equals 6. By the way, I can tell you right now my line is off. Why am I saying that my line is off? What's this say the x-intercept is? What's this say the x-intercept is? What does it look like? About 4.5. Is the x-intercept 4.5? No, it's 6. So that line is slightly skewed. And why? Because that point is probably not precisely on the grid. Because I had to go off my graph paper.
How did you get the negative x?
I subtracted x from both sides.
Okay.
To solve for y. Now this tells me, if this is right, and God knows I don't know if it is, that this says that x equal 1, y equal 5. That's my solution. And so now I need to perform a check. If x minus y equals negative 4, is it true that 1 minus 5, is that equal to negative 4? Whew. I worked for that one. And then I have, now notice, I went to the original equations. Why would I choose to go back to the original one and not the ones that I used for graphing? why would I basically go back over here? Because here, this is, I put this in y equals mx plus b, right? But why did I go back here to check my answer? What could have happened when I solved for y? Could I have made a mistake? I got the right answer, but to the wrong problem, right? To the one I worked, I got the right answer. So I go back to the original, exactly how it's laid out, and use it, because it's going to be a solution to this. So this says that 1 plus 5 should equal 6, and that's true. Boy, I lucked out that time, didn't I? Even though my graph was off, I lucked out. That's why graphing these things is not real accurate. So you don't want to do the graphical method necessarily to solve this thing. Oh, and maybe check your answer. Sometimes it's fun to graph, maybe.